It's my pleasure to introduce Brandon Buscaino. Brandon's coming to us from Sienna Corporation, where he's been. I've actually been collaborating with Brandon the past couple of years. We've been working on using their optical modems for imaging and sensing, and he's going to talk about, I think, give us some background on what's happening at Sienna and some really exciting applications of the technology. Actually, Brandon and I started our PhDs. We just realized this, I think. We started at the same year, at the same time at Stanford, in the same department. And we took the qualifying exam at the same time. Yeah. So we were kind of commiserating together. He was in Joe Kahn's group, graduated with his PhD in 2020, and then I think it's been at Sienna since then. And Brandon's also, he's been doing some really exciting research in optical communications, optical modems. He received the Kaminow Outstanding Early Career Professional Prize from Optica. Really excited to have him here and hear what he has to say. So please join me in giving Brandon a warm welcome.
David, I'm very excited to give this talk. I do know that some of these topics might be foreign to the people in this room, but I hope you find them interesting. My plan is to give you a little bit of a background on the history of the optical communications industry, just a brief one, and then talk about what some of the latest innovations in optical communications are. And then we'll talk about maybe some other different applications where we can use our modems for things other than sending bits. So as you are well aware, bandwidth demand has continued to grow at staggering rates. Particularly cloud growth has been extremely tremendous. Almost 20% compound annual growth rate for spending, and we typically see 70% increase of mobile traffic. These numbers are a few years old, but they're still really important. And the past few years, there's been a really heavy emphasis on data center operators scaling the bandwidth of the data centers internally and also connecting between data centers. So Sienna works on a lot of different links. So we build our products to span any type of link, whether it's a few kilometers long or if you're going through the entire Pacific, for example. So we do plenty of trials. This is a map of all of the submarine cables currently operating right now, or at least as of whenever I took this from Submarine Cable Map. But you can see that these cables will extend across the Pacific. And some of our recent trials, we've sent one modem across these cables, 1 terabit per second across the Pacific, for example. And we can send on any given wavelength, we can send 1.6 terabits per second on a single wavelength across many of these links. But that's a little bit forward. I'll maybe talk a little bit about the two big innovations that I would say that enabled optical communications, which are 1, the laser, and then 2, optical fiber. Now, both of these technologies, in their infancy in the 1960s and 1970s, had either were very large, for example, for the laser, or optical fiber was typically multi-mode optical fiber. While that was great for short distance links, multi-mode optical fiber actually has multi-mode dispersion, and that limits the reach of optical fiber in many applications. So throughout the 1980s and early 1990s, breakthroughs in laser design were critical in order to enable fiber optic communication. So the initial lasers were designed in the visible, so usually red, if you've ever seen a red laser pointer, right? But now we use only infrared wavelengths, so invisible to the naked eye, but they still can be dangerous, so don't look into the fiber. Another aspect is integration of lasers. So semiconductor lasers are now the standard, and they also allow for single mode operation. So I mentioned that earlier, but what's really important is that you're not propagating in multiple spatial modes as you propagate in optical fiber, because each of those spatial modes can travel at a different rate, and if you try to detect them at the receiver, you get an all jumbled up signal, basically. And similarly, like here, this single mode fiber here, this ultra low loss, which initially the first fiber that was created was on the order of 20 dB per kilometer, or even higher, and now the latest fiber designs will allow 0.2 or less dB per kilometer, so you can go 100 kilometers and experience less than 20 dB attenuation in your signal, which is crucial for enabling these links across the Pacific and the transatlantic, where you need to amplify your signals as well, but it still enables that very low loss transmission. And there were a few different big problems throughout the 90s and the early 2000s related to scaling optical communications networks. The first one is we were reaching the limits, and we still currently are reaching the limits with electrical bandwidth. So we can only send, well, back then it was the electrical bandwidth that you could operate with was several gigahertz, but you wanted to send more information on those channels. And so a whole host of technologies were developed related to sending multiple wavelengths on a single optical fiber. So the solution was wavelength division multiplexing. And here you can see we have, you can now send on a single optical fiber 10, 20, 50 different channels that are optically multiplexed and demultiplexed onto a line system to ensure the capacity was increased here. So this is what say a typical line system will look like right here, where you have about 5 terahertz of the C-band that's being occupied by anywhere from 10 to 100 different modems that are operating along that line, sending information. But I'll tell you why in a second, why we're limited to those wavelength ranges. Another very impactful limitation for distance-wise is chromatic dispersion. So the different frequencies travel at different rates, at different speeds inside optical fiber. And if you send a large bandwidth signal, different portions of your signal will travel at different rates, and that will distort the signal. So this shows up here. This is perhaps your signal, intensity modulated signal there, and after transmission over several thousand kilometers, you basically get garbage, and it's very difficult to extract information out of that signal. So a whole host of technologies were developed on the optical and electrical side to compensate for dispersion. On the optical side, people shifted, instead of using 1500 nanometers, they went to 1300 nanometers. That's where the dispersion 0 point is in optical fiber. And that ensured that you get less dispersion, right? Or there was, here is a dispersion compensating module here. This is an optical fiber that's specially designed to have the opposite dispersion characteristics as the link in front of it. So you can use these different types of techniques for dispersion compensation, and particularly for intensity modulated links, which is everything was intensity modulated, simply varying the power of your laser and sending those bits that way. But we'll talk about in a minute a different way to approach the problem. And finally, the absorption loss limited range, even at very silica fiber, to this 0.2 dB per kilometer. It turns out around 20 dBs of span loss is roughly what you want between your spans for a wide variety of reasons. But you want to go 1,000 kilometers. Typically, what you would have to do is you'd have to use an optical to electrical to optical repeater. You would detect your optical signal, convert it to an electrical signal, process it further, and then resend it on another laser, co-located laser, right there at the repeater site. Well, in the 80s and 90s, erbium-doped amplifiers were developed, and these allow for optical to optical, so just simply amplification, eliminating a very difficult process, which is that O to E to O conversion. And now with the erbium-doped fiber amplifiers that are pumped with the laser diode themselves, you don't have to worry about all of that detection and transmission at every node. And so in 1985, we were sending 500 megabits per second over 400 kilometers. And now in 2020, right across the Maria transatlantic cable, which is actually packaged with 8 separate fiber pairs, you're looking at 20 terabits per second on each of those fiber pairs, so with a total capacity of 160 terabits per second. And that would not be possible without optical amplifier technology, but it also would not be possible without coherent optical communication. So in the late 2000s, the coherent revolution happened, and I promised David that I would give one wave optics slide for everybody here. So you probably are familiar with amplitude modulation and amplitude detection, right? You send out bits, you modulate the amplitude of your signal, and like a 0 and a 1 bit is 0 is no power, 1 is full power. But optical fields have additional orthogonal dimensions. So they act as waves. So they have both amplitude and a phase. and as well as they have multiple polarizations. So what we can do is we can encode information on each of these different dimensions. So this is what. This is an example of an optical field propagating in time here. Each of these corresponds to a symbol period, and in each of those symbol periods, we can both separately modulate the phase and the amplitude of the light to encode bits onto onto each of those dimensions for both the x polarization as the wave propagates through the x direction, and the y as it propagates through the y direction here. And this is represented as an IQ plot. I'll show a few of those later. It's just a representation of the two orthogonal dimensions. The in-phase, they stand for the in-phase and quadrature. They roughly correspond to the orthogonal dimensions of amplitude and phase. And so in this case, you can also, instead of modulating zeros and ones, you can do 0, 1, 2, 3, increase the modulation order as well, in order to increase the total number of bits that you're sending for every symbol. So with this technology, with coherent technology, for the same electrical bandwidth, you can now send 4 times as much information because you've unlocked these 4 orthogonal dimensions. Of course, you're introducing a lot of noise when you do this, but there are ways that we compensate for this. And one of the most important features of coherent detection is with the coherent detection, which I'll show in just a second here, you're able to linearly, estimate the linear field. Intensity modulation and intensity detection. When you do intensity detection, you square the optical field. And that is why you don't get that information in the phase. So now that you're detecting the linear optical field, you're detecting both the amplitude and phase, you can correct for any linear impairment. One of the big linear impairments that we correct for is chromatic dispersion, that when those different wavelengths propagate, with those different frequencies propagate through fiber at different rates, that's a linear effect that can be undone digitally in the digital signal processor without the need for any optical dispersion compensation modules, or without any other operating at wavelengths that have lower dispersion. So it's a very large advantage, and allows us a lot of flexibility in the digital signal processing. So this is what these are the building blocks of a coherent transmitter and receiver. And so right here in the dash box here is what we call our digital ASIC. So a typical digital ASIC for a modem will be composed of both a transmitter and receiver side, and it will perform both functions, and it typically is the workhorse of the entire modem. So you'll have bits coming in here. And we do, you may be familiar with different types of encoding schemes. What we do is we'll do digital filtering in order to pre-emphasize anything in particular that we know is going to happen along the link or in the transmit side of the modem. And then we'll convert those digital signals to analog. And on the similar side, when you're receiving a signal from a remote location, you'll first do analog to digital conversion, and then you'll do digital filtering, which is typically an adaptive digital filter that's used to correct whatever impairments that optical signal received along the fiber. And then you have stages of clock and carrier recovery, because the lasers that you're using and the clocks that you're using at these modems are not synchronized. So you estimate the clock and carrier phase that was transmitted. And then, of course, you need to derotate your polarization, because in single mode fiber, while X and Y polarizations propagate through the optical fiber, they are orthogonal, generally. It turns out that when you receive the signal, you don't know the orientation that you receive relative to your transmitter 1,000 kilometers away. So you need to derotate those symbols as well. And then you do your modulation and decoding. So this is the digital ASIC portion, but there's also a lot of analog electronics. So you have your RF gain for your modulator drivers, and then you also have transimpedance amplifiers after your photodetection. And then there's also the E to O and the photonic stage, which is we have our integrated transmitter electro-optics and the integrated receiver electro-optics. Those are composed of things like the tunable laser, as you can see here, the modulators, the receiver, which is composed of a coherent optical hybrid, which is a sequence of different waveguides with phase shifters that interfere the light to perform the coherent detection, which is really, really fun to write those equations out, but I don't think we have time here. And they all come together, and it looks something like this. This is our WaveLogic 6E modem. And you can see, well, why don't I want to put it here? This is one of our transmitter boxes, and this is the receiver box here, and this is where they sit inside the modem. This right here is the digital ASIC, this gray part right there. And so, and then there's also a lot of the PCB that it sits on, and then there's also quite a lot of other optical equipment. For example, this is actually an amplifier, an erbium doped amplifier that's integrated into the unit, so that we are sending the correct amount of output power. And each of these units is designed in house and at Ciena, and in many cases, we integrate it all, and we build almost all of it ourselves.
What's the physical size of that green box?
Yeah, it's about this big, like maybe I'd say 15 centimeters roughly. So it's pretty small, and the plugs, which one of which David has in his lab, is an even smaller form factor. That's in what we'd call a QSFP-DD form factor, and that's about that size right here. So I guess we can talk a little bit about what has driven this technology forward over the past 15 years. And without a doubt, one of the most impactful drivers is the progress in CMOS integration. So the power consumption has drastically reduced with different nodes as we progressed into different technologies. And then also the total cost of fabrication of these dies is very important. So that has dropped dramatically. So these two have really created an environment where it makes sense for us to scale our technologies. These technologies can now support lower power consumption. So with a big indicator is a very big metric is power per bit. So if we want to double the bit rate, we need to have the power per bit to ensure that we're operating at the same power envelope. And there's no doubt that the advancements in digital ASICs have really improved and enabled the scaling of our modems across the years. And this is reflected in the total capacity that we've shipped, as well as the power per bit, the total power consumption per modem per bit. So we've over the past 15 years, we've improved we've reduced, I should say, the watts per gigabit per second by 90%. And so the last on sort of this history, at least, there's several of these slides for other companies, but for Ciena in particular, this is the generations of our digital ASICs. So we started designing digital ASICs before coherent technology came around, because our first digital ASIC that was released in 2005 operated with intensity modulation, but had built-in electrical dispersion compensation. There's pre-compensation. There's ways to pre-distort your signal so that when you know it as it propagates through the optical fiber, it undistorts itself at the receiver. But starting in 2008, that was the first generation that we have, and you can actually tell that this is an intensity modulated signal based on the very strong laser spike. That's the DC value of an intensity modulated signal there. And then as we got to other generations, you lose that spike because they're coherent technologies. And so right now, our latest platform operates at 200 gigabaud, so over 200 gigahertz of electrical bandwidth, and can send 1.6 terabits per second over many links, hundreds and hundreds of kilometers. And I'd like to talk a little bit about the technologies that we implement inside this modem to enable it to send that information. So this is another marketing slide here, but this is again the modem here. This is a layout of the ASIC, and we rely on the 3 nanometer FinFET CMOS for 6E, and again operating at 100 gigahertz bandwidth, and that really unlocks a lot of potential spectral efficiency. So one of the first big advances, and this is not new to WaveLogic 6E, is constellation design in particular. I mentioned earlier how you can design your modulation formats so that you can exploit multiple dimensions of light, so in phase and quadrature, amplitude, phase. But you can also optimize the modulation format for a particular channel. When we sell a modem to a customer, we don't know if that customer is going to be transmitting over 100 kilometers, over 500 kilometers, or over 10,000 kilometers. They can, we usually talk to them before, but we need to design one modem that is capable of transmitting across all of those. And one big advantage that we have is probabilistic constellation shaping. So right here on the bottom, you can see this is effectively the transmitted distance, and this is the achievable information rate in bits per symbol. If you're sending a fixed constellation, there are certain distances at which you are either your margin is way too high for that link. You're either sending it the wrong total number of bits per symbol, and this is can be seen by this step function here. In addition, you're also the optimal channel for many fiber channels results in a optimal. There's also a matched distribution of your modulated symbols that will be ideal for that channel. And very frequently, that distribution is the Maxwell-Boltzmann distribution for these signals. So what we can do is we add in probabilistic constellation blocks into our DSP modem, and what they do is they take a fixed input line rate and they map them to deterministically to symbols that have the correct probability distribution that's desired here. So you can see that instead of sending bits equally in each of these points on the IQ plane, you can send more bits in the lower power points. And what that does is you effectively decrease the total average power that you're sending, or in other words, is you're effectively increasing the maximum spacing between two adjacent points because you reduce the power, but you also scale the constellation. And so this actually gets you a pretty sizable amount. It gets you on the order of 1.5 dB. So that's, again, close to 50% farther distance that you can achieve. And this is all done, implemented in the digital ASIC. Then, of course, we can think of other modulation formats. Okay, we exploited polarization. We've exploited amplitude and phase. Why not exploit time? Why not design our modulation formats so that one symbol can be distributed across multiple time intervals? And when you do this, you get these sort of crazy-looking symbols, but these are for really difficult, really challenging links. You're sending effectively one bit every 2 symbol periods in this case. And what you're doing is you're spacing, like the whole idea behind constellation design is you have some noise, you want to space your points as far away from each other as possible, so that when you try to detect which point you sent, that they're far enough away and away from the noise doesn't confuse them. So why not send them in time as well? This allows us to send there's really difficult links that can be sent, very difficult nonlinear links that can be sent with multidimensional modulation formats. In addition, very long links also have nonlinearity. So optical fiber is a very good medium for transmission, but accumulated over many thousands of kilometers, hundreds or thousands of kilometers, you can get nonlinear effects. And in particular, if you send, this is an example here of sending a constellation, a 16 QAM quadrature amplitude modulated signal, and at the end of the link, with some additional noise but lots of nonlinearity, you get a nonlinear phase rotation in the symbols. And that obviously, if you're looking at trying to detect these symbols, that introduces a lot of errors. What you can do is you can pre-compensate those symbols beforehand in order to such that after they propagate through the nonlinear channel, they look a lot cleaner. Now, this is a lot trickier than it looks. The reason is nonlinearity depends on the actual sequence of symbols that you are transmitting in a given time window. And what that means is you need to, and you do not know what symbols you're going to receive. Someone tells you to send some data, and you have to send that data, right? So in that case, you have to be able to, on the fly, compute how you need to distort your symbols as you transmit them so that they reduce the nonlinearity, which is challenging but effective. And finally, in nonlinearity mitigation, one of the reasons, one issue with nonlinearity mitigation is as it accumulates over time, one important feature is the relative phase of different frequency components as they transmit through optical fiber. And if you have one single signal, those all of the frequency components in that big signal, for example, this large bandwidth signal here, all of them can effectively are in phase, and so one way to think about it is that they're in phase, and what this results in is an increased nonlinearity. But if you split up your channel into multiple frequency FDMs or frequency division multiplex channels, then this does two things. It reduces the amount of effectively phase matching between the different frequency components, reducing the nonlinearity. And it also smooths out the signals. You get a nice smooth signal, and not highly nonlinear signals do not like large peaks in time, which you might have with a single signal like this. And so for very challenging nonlinear links, frequency division multiplexing helps. Frequency division multiplexing is also very useful for a lot of practical applications where you're multiplexing, like most networks in the United States or in North America or wherever, are composed of many different ROADMs, which are reconfigurable add-drop multiplexers. All that means is you have a modem here in Wichita that wants to connect to Toronto, and it might go through 10 or 20 different spans, and in each of those spans it needs to go through a central hub and get routed onto a different way. It stays on the same wavelength, but get routed through these hubs. And what's one challenging aspect is that in each of those there's filters. And so if you propagate through 20 of these filters, all of a sudden the edges of your signal can get really attenuated. And so what you can do is you can actually send less information in those channels that get attenuated, but push more information into these channels with your probabilistic oscillation shaping engine that you have. And thus you can match your data rate, your channel, and these FDMs allow you to do things like that. And finally, I'll talk about just two other things that we have in our product, which I don't think it makes sense for me to talk about the details of these, but I will say that typically when you're looking at a communication system, we're limited by the Nyquist sampling rate, but typically a lot of systems have some roll-off. That really helps with clock recovery. Well, we've designed in our system edgeless clock recovery to increase the spectral efficiency. So now you can place these in your WDM grid very, very closely. The only guard band that you really need is to ensure that the center laser doesn't drift into another channel. But other than that, you get exactly as much information all that information is contained in that exact bandwidth. And finally, this is a quite difficult feature to implement and integrate, but we can actually do in-service baud tuning. So we can, while you're transmitting a signal, we can change the symbol rate without any hit to the actual data carrying traffic, which is a lot more challenging than it might seem. Okay, so this is what we've done and accomplished, but what is going on now in optical communications that people are really talking about? Yes, yeah.
So I was just trying to understand. So the modems themselves, when you connect them to your, let's say, 1,000-kilometer fiber, do you know in advance the properties of the fiber, or it is measured on the fly, and then that information gets exchanged so that you can calibrate everything?
So sometimes you'll know things, like a lot of network operators will have characterized their fiber systems, and they'll say this link delivers an optical signal to noise ratio of roughly this. And so then in that case, that means you look at your table and you say, okay, well we can send about on that link we can send 1 terabit per second instead of the 1.6 terabits per second because there's too much noise. So they'll configure it in a mode usually that's where the margin is appropriate for that. So they'll have some prior knowledge. But we have lots of cases where you want to operate with some margin. So we have lots of cases where you might provision it with very low margin, and then we will adaptively improve to get to the correct that correct margin. Like, we're not always at the optimum immediately, but we have different ways that we adaptively improve the channel estimation to bump up to reduce the bit error. Oh, and also I haven't mentioned it, and this is an incredibly important feature. We do not try to hit bit error rates that are the final bit error rate for the line system. So all of these modems need to operate at bit error rates of less than 10 to the minus 15. So you're expecting a bit error of less than every month or less, right? But the reality is when we're sending these symbols, if you look at some of these symbols here, we can still close a link with some of these. It's different data rates. And the reason is we have forward error correction schemes that wrap the entire system. So for us, we have we operate at a bit error rate that's I can't tell you, but is like, a percent or whatever is very high. And then that's all cleaned up with our proprietary forward error correction algorithms. And that way, that's a way for us to approach the optimal capacity of the channel. Okay, so what's next? There's a few different things that I'd like to talk about here that I think are really interesting. One thing is that optical communications is now changing, and I will send this out to David. I just wrote an article in Optics and Photonics News about how coherent optics is moving to shorter and shorter length scales. And I want to spend a little bit of time on this plot here. This right here is the historical trends of the transition point between copper and optics. And so right here, this transition point is around 100 gigabits per second times kilometer. So in the early days, when for distances of 1 kilometer, hundreds of kilometers, thousands of kilometers, that transition happened at relatively low data rates. But as we've been seeing the need for an increase in link bandwidth, we've been noticing transition from copper to optics at much lower distances. And the reason for this is that copper is generally lossy at high frequency. So when you're transmitting electrical signals at high frequencies, they experience a lot of attenuation. Because optics does not have that feature, it's very flat attenuation and very low consistently across the entire bands that are being used. It's very desirable in that case. Now, you have to go through, of course, the electrical to optical to electrical, because we don't have optical processors, well, yet, or I don't know how people have been talking about them for a long time, but I don't know if that'll ever happen. So that's one trend that's happening, and that's why we've now seen, especially at Siena, even coherent technologies are now entering the data center. So low power coherent technologies to interconnect AI or machine learning clusters inside data centers, between data centers, they're very common. And similarly, there are other technologies here of putting the optics closer and closer to the electronics, right? And this is the same principle, right? You want to reduce the amount of electrical distance that you have to transmit high frequency signals on, because that's just power, that's just loss, that's loss in your link. And so right now, this is the typical pluggable technology, where you essentially slot a pluggable into the faceplate of your switch. The optical to electrical conversion happens here, and then you go across electrical traces on a PCB to a switch in a switching node, for example, in a data center, and then that's where the switching happens, and you get sent to another different connector. Whereas in different iterations of this technology, with pluggable optics, and now so eventually moving towards fully co-packaged optics and electronics, you can imagine having the fiber extend all the way to right next to the ASIC, and then have it converted to the electrical signal for processing. That's the goal for the co-packaged optics supporters. There's a lot of challenges in integration, and I could talk with you a long time about that. But so this is like what it might look at, like a co-packaged optical system is a mock-up of that is up there. But there are also other interesting applications going on right now. So lots of different types of fibers are being developed. I mentioned that multi-mode fiber was very difficult because it introduced all of this multi-mode dispersion, and the signals get mixed together. Well, okay, all those signals are being mixed together, but it's a linear mixing. And so in theory, if you have enough modems that are coordinated enough, you can do multi-input, multi-output, and you can increase the capacity on the order of the number of modes in fiber, of the particular fiber that's designed. Or you can send them in multiple cores and multi-core fiber. Or very recently, there's been some announcements in hollow core fiber now, where hollow core fiber, where the light is actually propagating through air inside the optical fiber. So it travels faster than in silica because it's traveling through air. And also because it's traveling through air, it's not attenuated by the silica. Now, these cables are more expensive to design and manufacture and maintain, but this has been a very important, very exciting field for the past 5 or 10 years. And then we also have demonstrations on quantum secure channels where we've done quantum key distribution between our actual wave center systems, quantum securing different channels. So this is again coming, but it's an important feature. And another very interesting thing, which I was talking with David earlier, and I've been working on this myself recently, is the idea of using optical fiber as a distributed network. Now, I mean, there's been lots of work on this over the years for earthquakes. You might have heard Google made an announcement maybe 3 or 4 years ago where they used their undersea cables to detect earthquakes. What happens is actually undersea cables, it's really quiet down there. There's nothing down there. And so when an earthquake happens and actually shakes the cable, you can detect that in the state of polarization and then at your modem. And then you can take that back and you can triangulate where an earthquake might have happened, for example. But there's lots of applications where things are a little bit messier. There's traffic. There's someone trying to dig near your cable, and you want to be able to detect whether someone's digging near the cable. I saw this one customer was interested in like the differences between like backhoe and I mean like someone digging with a shovel near their cable, and all of this. The world has quite a lot of different types of disturbances that can be sensed with optical fibers. And so we have a test bed up in Ottawa, and we've which is composed of several spans of optical fiber, 5 spans of optical fiber, with amplifiers in there, and we have some different types of instruments in there. And one of the instruments that we have is a piezoelectric tube. It's a fiber stretcher. You just apply a voltage, and it just stretches the optical fiber to simulate a phase disturbance. And so we can, if you look at the phase and frequency noise here, these are different disturbances that we've generated. You can do 500 hertz, 1 kilohertz, 2 kilohertz. And what we showed is over this 500 kilometer link in the lab, for a 2 kilohertz disturbance, we were able to get 10 meter localization on where it was. Really limited to how well we know our own fiber link. And this is enabled by the fact that we have 2 wavelength 6E modems that are able to stream carrier phase with timestamps to a central processor that we're able to cross-correlate where this event is happening. So really, we're able to get really fine results in the lab. Okay, when you start looking at real-world events, it becomes a little bit more challenging. So here's one of our EDFAs in the system here, and so this is someone made this impact hammer at Siena 20 years ago. It gives a nice calibrated a certain amount of newtons that's like that, basically. Like someone slaps the EDFA. Okay, well, how well can you sense that? And if you use polarization, okay, not very well. 400 kilometer accuracy on a 500 kilometer link, good luck. If you use phase, now you're talking kilometers. You know, sometimes you're getting close, sometimes you're not. It really sort of depends. But that's what real world vibrations do. Sometimes they're small, sometimes they're large. Classifying them, understanding them, I think is a really interesting field right now. So, and there's lots of data. People are collecting a lot of data on this now. And I guess the one other topic that I wanted to talk about is free space optics is also something that we've been involved in, and we have some programs on. There's a lot of applications for terrestrial applications where you're going maybe several kilometers between buildings, last haul applications. You probably heard, or you may have heard, there were some companies doing airborne aerial vehicles like Google and Facebook were trying to use them to, serve internet to underserved areas. And then there's also, of course, big satellite constellations. And so we have an internal, free space optics program where we look at some of these ideas. And what I've what I've been looking at in the lab is so these are actually lab data that we have where we have a turbulence emulator, and what we're doing is we're actually doing multi-wavelength transmission across different channels. And I don't have enough time to go. Well, I mean, I guess I can go through it a little bit, but the general idea here is if you send correlated data on different types of channels, say on 2 different wavelengths, for example, across a turbulent channel. In this particular variant, which we're working to try to enable, if the signals are the same and sorry, let me step back a second. Optical signals, when they propagate through a lot of air, experience turbulence. Now, they don't experience attenuation. The power levels are the same, but you're probably very familiar with the speckle. There's a significant amount of fading that is induced on a given channel as it propagates through the atmosphere, depending on how much turbulence it experiences. So if you separate your wavelengths far enough away from each other, you can decorrelate the statistics of the fading. And if you're sending the exact same information on those two same wavelength channels, then you can ensure that the outage probability is relatively low. Because if one of the wavelengths goes down, you still have the other one. And so we have some ideas of how we can do this in a single modem, right? This is what these are the initial stages of what I've been showing here. But there are certainly some challenges involved with the actual theoretical wavelength correlation, right? You need to separate your wavelengths really far away from each other to get good decorrelation. Yet, this design, we want to use a single modem, so the electro-optics need to be capable of supporting those different wavelength bands. So there's a lot of sort of interesting work that we're doing on free space optical, not just wavelength diverse. In a lot of cases, customers who want to buy optical links for their satellites will want to buy a pluggable form factor where the power consumption is really low, but it can send hundreds of gigabits per second. They don't care about sending the exact 1.6 terabit per second, the maximum capacity. They want a low power, low size weight power for airborne or satellite applications. Okay, so I promised only two more slides, and part of the reason I'm here is because we have a collaboration with David and Kiros at Siena, looking at things outside of the actual optical communications that we can use our modems for. Fundamentally, what we do is we transmit an optical signal, and then it gets distorted, it gets impaired, it gets attenuated, and then we receive that optical signal and we try to extract the maximum amount of information as possible from that signal. That's true for a lot of other things. One project that we have is on diffuse optical spectroscopy, and I mean, there's probably people in this room who know a lot more about this than I do. But I know that there are people in this room like that. But if you look at the across different wavelengths, different types of tissue and different components, oxyhemoglobin, deoxyhemoglobin, lipids, they all have different absorption and scattering properties. And so if you analyze how light propagates through that tissue, you can then extract those absorption and scattering properties out. Well, one way to do this, and this is just one way, is with the spread spectrum technique. That's where you modulate the light before you put it into. In this case, this is a head monitor where the light propagates through the tissue and then is collected by a receiver where it's then digitized. And then you take those signals and you cross-correlate them. So you cross-correlate the transmit and receive signal, and they have the exact same. They're the exact same signal. You should see a nice peak in the middle. It says this is where this is the delay of the total delay of your signal. But if diffuse in this diffuse spectroscopy, when there's lots of scattering, what happens is those symbols get spread over time. And so what you end up getting is not a nice sharp peak, but you actually get a sort of a temporal point spread function. And by using models related to optical transfer through scattering medium, you can extract different properties of the tissue, like the absorption and scattering. And so we've done this. We got one of these tissue phantoms from Politecnico di Milano with some, nicely designed at 1550 for us who are working in telecom wavelengths. Most of these people only care about the near infrared for now. For this particular application, I'd say. And we were getting ballpark, with very short exposure times, because we're continuously detecting these optical signals, we're able to get pretty reasonable errors in the scattering and absorption properties of these phantoms. So I guess that's one of the applications. And of course, we have the application that we have here at U of T. So you've probably seen this, or you may have seen this, where we have where Parsa and now Dongyu and everyone's been working very hard to get these modems configured into a LiDAR setup, a coherent LiDAR. And now we're able to do 2 millimeter ranging resolution. We can do Doppler imaging as well, simultaneous velocity estimation as well as ranging. And the current work is working on different types of polarization sensing. So this is a very interesting application where With a coherent modem, you're able to extract all of the properties of the light. You're able to get both the phase, the amplitude, and the polarization. That's naturally extracted from our modems. So the goal is, well, can we range? And the answer is yes, and we can do it pretty well. And now the question is, well, where do we go from here? And that's not for me to say, but for maybe for David to say, Pierce to say. Okay, so that's what I had. I wanted to thank all the people at Siena who contributed to these slides. Yeah, and I can't say this strongly enough. I've really enjoyed working at Siena, and if anyone else is interested, please do check out our careers page. We're a very large company. We have locations all over, a ton in Canada, several in the United States. We'd love to have you. We do all sorts of software, so just don't think that if you don't do any hardware that you wouldn't be accepted. We have more software engineers than hardware engineers probably. So yeah. So thanks again for inviting me.
Great. Yeah. Thanks, Brandon, for the great talk. We have a few minutes for questions. If there are any questions?
Yeah.
Yeah, thank you very much for your talk. I had a question about the application of space optics.
Yeah.
So you're talking about it's going through air and then there's some turbulence. I guess would that be like I'm assuming that's like scattering is you're concerned about there?
So it's actually the physical issue is that what happens is when you hit different pockets of air that have different temperature, their index changes. And so what ends up happening is the phase wavefront of your beam gets distorted. And when that light then gets collimated and coupled into a single mode receiver, for example, you're effectively summing or interfering perhaps in phase components. And so that so effectively then what happens is it results in a drop in the power of the coherent signals. Yeah, so it's typically not scattering. I mean, like there is lots of scattering in like fog, I guess, but like clear air turbulence is what we're looking at here. Yeah, that's what it's called, clear air turbulence.
I see. And so then there's some phase compensation that you do to account for that.
So there sometimes there's actually, and I don't think I have a slide here, but there are some ways of doing this with spatial diversity, and the idea could be that like the most common one, I guess, it involves like essentially compensating for the wavefront. It's called like adaptive optics techniques, and essentially you have like in some cases you have like a micromechanical mirror array, and you effectively estimate the phase distortion of the beam and then correct it before it gets coupled in, and that can improve it. Those systems can be quite expensive, I guess. That's sort of but they do work pretty well.
One quick follow for the sort of like head monitoring system you had. You mentioned this one. I guess the main thing you're dealing with is when it goes through the tissue phantom. The main sort of the distortion you're dealing with is just scattering, not absorption, right?
Well, absorption is a pretty big issue also. So like I guess the absorption is important when comparing multiple wavelengths as well. But for like a single, if you're only operating at a single wavelength, you can fit to both the absorption and the scattering, but you need like calibration, I guess, for it to be useful. But the scattering is what effectively spreads it out, right? Yes, yeah.
When we were talking in the first third of the talk about polarization and coating, we were saying more fibers. Do you have to worry about strain by refringence as it goes through?
Yes, yeah, you do. So there's that's a great point. So yes, we do. And so our modems account for different types of dispersion. So in particular, with polarization, you have polarization mode dispersion induced by refringence. This can be corrected by different time domain adaptive filtering because it's a linear process as well. And so typically in different modems that it's handled in different ways, but sometimes it's done in the frequency domain, and sometimes it's done in the time domain. In this case, you just need to make sure that if you have these polarizations that are walking off from each other due to polarization mode dispersion, you need to be able to have a time domain adaptive filter that is long enough to correct for that. And so we have specifications. I mean, it's built into like say a time domain linear adaptive filter in our system. That's also, yeah, so that's true for first order, second order polarization mode dispersion. It's also true for any of the other chromatic dispersion that we have. There's also a few other functional blocks that I didn't mention, or I didn't focus on, like the clock recovery is a very important aspect, right, of the digital signal processing. But yeah, it's true that there is some, I guess, there is some walk-off between the two polarizations occasionally. It's just, we can correct for it.
And you have to know what they are before you design your time domain compensation, or what's
yeah. Right. So there's also, well, I guess there's there's not only just polarization mode dispersion. There's also like polarization dependent loss, for example. That is quite and that actually that would be is most commonly statistically characterized rather than like deterministically once and characterized. In those cases, for example, polarization dependent losses actually does result in a penalty. There are ways that we compensate for that, but that penalty can be characterized. Typically, a network operator will know how much PDL is on their link. With polarization mode dispersion, we can compensate, but the PDL you can't, and so then that's something that you would like polarization dependent loss. So that would be, for example, if you have a kink in the fiber and it's mostly affecting one polarization, or more likely what happens is in one of your network elements, there's a particular component, like basically in these ROADMs that I mentioned, these hubs, frequently for the demultiplexing, they'll break them out into free space, and when they do that, there could be an element that has higher polarization dependent loss. And what that does is the network elements, they don't do any sort of they don't know about the polarization that's being transmitted. And so if you introduce polarization dependent loss and one of the channels is now, one of the polarizations is a lot lower, what ends up happening is you amplify it to a certain average power. But what that means is that one of those polarizations is now dropped down by a factor, a certain factor. So when you're trying to receive it, it's, one polarization has plenty of power, the other polarization has much less power, so the noise is a lot higher in that channel, and that'll be a penalty in your margin, for example. So that some things like that is we just budget for, and other things we can correct as linear movements. Yeah.
I'm not sure if you can say which companies does Ciena compete with, and what are you competing for in the future?
I probably shouldn't say who our competitors are, but I think that one of the biggest markets right now is the data center market. So that is really there's a lot of competition in terms of actually two competing thoughts on how optics will scale inside data centers. I mentioned two of them, which is whether the transition will be made from intensity modulation to coherent detection, whether I guess I should say the hyperscalers or the switch designers will choose to do further co-designing of optics and photonics really close to each other, in which case that would probably mostly be intensity modulation techniques. But those ecosystems are vastly different as well, because right now the current data center ecosystem is involved shipping high volume of pluggable optical devices. And those are made, lots of different companies will make them, and they're designed to be as cheap as possible and for them to manufacture as many of them as possible. But right now, because intensity modulation and intensity detection is reaching a limit, you either have to compensate that with coherent, or you have to compensate it with reducing the electrical interconnect distance. And one technology that I did not talk about here, but made the news, I guess, a few years ago, was optical switching inside data centers. So basically, right now, a data center is composed of many different switching nodes, and in those nodes, you have basically, again, optical to electrical to optical. They route you to a different server inside the data center. With optical circuit switching, which Google demonstrated in some of their data centers recently, they're actually it's again all optical switching. And it requires a complete rework of the design of the network because most data center networks are based on IP traffic and it's packet switching, whereas they can't do packet switching at the speeds. They don't have the speed to do that, and so they had to redesign their network to be able to, as a hybrid network that supported some packet switching and other more orchestrated switching. So that's another discussion. I think that a lot of other Google said we did it, and then they said we made these switches. Now can someone make them for cheaper? I think that was sort of the idea behind that. But there's a few different technologies that are really intersecting right now in the data center that are pretty interesting. Yeah.
I had a question about the distance spectrum.
Yeah.
I was wondering, you mentioned that you usually use telecom wavelengths. I was wondering what limits you from connecting different lasers to your system. Like,
Yeah.
is that something that you could do to get it accurate?
Yeah. So that's a good question. I guess there are a few limitations. A lot of the infrastructure for us is we have erbium doped fiber amplifiers. And I failed to mention this earlier, but the reason why most long haul WDM transmission systems are limited to that 5 terahertz, which is called the C band, and 195 terahertz, is because that's the optimal bandwidth of the erbium doped amplifier. That's the gain bandwidth to which the erbium doped amplifier works really well, and it's a very efficient technology. There are really not limits to working at other wavelengths. We've explored, at least in principle, going down into the near infrared. The issue is it's just a lot of development for when all of our telecom products would be built in 1550 because they would operate at which 1550 nanometers is the the absorption minimum for optical fiber, or 1300 because that's the dispersion low for optical fiber. Though we don't care about it that much, the dispersion for that. But like people who use almost all data centers operate in the O band at 1300 because their intensity modulation to minimize that chromatic dispersion. So yeah, there's no limitations.
And the erbium amplifier is
1550.
core to this working.
Yeah, so having a lot of power really helps, right? There's so much loss. You're looking at loss when you look at these fibers that are connected to this phantom. You're talking about 60 dB of loss, because it's not only just that it's that there's loss and scattering in there. It's also that we're using single mode fibers, and single mode fibers have a much smaller admittance cone, effectively, to be coupled into the fiber, and so that really limits. That's probably 30 dB right there. Right. So with this implementation, yes. Now I will say that single mode fiber is the reason why you can do coherent detection at all. I didn't get into the details of coherent detection, but the idea roughly behind coherent detection is you transmit on a laser and you interfere it with the local oscillator, another laser, that interference is only possible if the polarizations align essentially in a single mode waveguide. And so when you can't do it with multimode. You can do it with multimode fiber. It's just going to be a lot less efficient. So that's why you can't, specifically for coherent detection, why you can't use coherent. So you get some gain there. But yeah.
When I started here, I remember there being a battle between satellite communications and long-haul fiber. Of course, satellite was not optical.
Yeah.
So you see optical satellite communications coming back. Is that detrimental to the fiber links we have on the ground?
No, from an optical perspective, no, it's not. And I guess, this is something that I think is a little bit of a flaw with the satellite systems. Is now all these satellites are being sent up, and they're being equipped with optical interconnects between them. And that's actually that's fine. They can operate at 100 gigabits, 200 gigabits, up to 400 gigabits right now with these low size, weight, and power modules, and they're operating in space, so there's no clear air turbulence. They're easy to hit to each other. But the second your interconnect bandwidth is hundreds of gigabits per second up there, but when you try to get downlinks to the ground from low Earth orbit satellites, you're looking at maybe a gigabit per second, usually on the order of hundreds of megabits per second. And so there's just a mismatch between the bandwidths up there and down here. And so I mean, that's what that's what some of these things are working on. If we could actually get an optical link, then we could start to make that make it a little bit more symmetric. But right now, it doesn't really pose a threat. And also, I will say that there are some demonstrations that have shown optical ground to satellite, but all of them, and NASA has a great program on this called the T-Bird program, and they actually use coherent modems. The issue is the way that they correct for atmospheric turbulence is with an ARQ protocol. So if they lose the bits and then they send it back up and say, hey, we forgot some bits, can you resend them? And so your latency is crazy. I mean, no one wants a latency of a second. There are some issues with like real time networks that are not going to be solved in the near future. I will say.
Very interesting.
Yeah. Mm-hmm. Yeah. Yeah.
So this, what you said, hollow core.
Oh
fiber?
yeah.
So is that free space then? Is it essentially free space optical?
Yeah. So it's free space in the sense that it's that the mode is propagating, like the propagation mode. A majority of the propagation mode occurs in air, but it's not free space. So there's no Gaussian beam optics where you'd see some spread like that. And I'm not an expert on this type of design, but basically these nested. This is called antinodal nested fiber, and essentially the very thin walled silica allows the beam. It basically shapes the mode profile of the optics and it basically ensures that the most adjacent modes that normally would be your light would use that to couple out of the fiber are impermissible based on the structure of the fiber. And so then if it can't go into those modes, it has to stay confined in that mode. And actually the floor of there's a theoretical threshold on the absorption loss of silica, and the hollow core fiber theoretical is a lot lower than that. I think it's very low. But there's a lot of again, I mentioned that the fabrication of this can be very difficult, and the way optical fiber is normally made is you basically take a big thick piece of silica, preformed silica, and you have a 10-story or higher building, and you heat it up and you draw the silica down to where it's very, very small. But when you do this, the preforms are really complicated, and you can only draw a certain amount of fiber. And it's still a very active research. There are fiber companies who would hear me say that right now, and they'd be like, "No, we can do it." Well, how much is it going to cost? Is a big issue. And also, if you have a break in the field, if this is laid out, normally you could send out a tech for single mode fiber who could do a single mode fiber splice in the field pretty straightforwardly, pretty easily. The alignment tolerance is a lot more difficult. I mean, they are now selling equipment that this exists now, but now you need to make sure these nested nodes align, whereas before it's just you just got to make sure that they're geometrically aligned. And people want to send a ton of power. They think, well, we're only in air. We're not limited by nonlinearity. Let's reduce the number of amplifiers, right? And send as much power as we can in there. Well, now there's issues with launching that much power. You've also got eye safety concerns with you need to make sure that fiber is secure, because you don't want someone accidentally digging and hitting a hollow core fiber and they get blinded or something. So it's a really interesting. There's a lot of interesting problems with it, but it's amazing. It's really, really very cool. So
great. Well, maybe we can stop there for the questions. But let's thank our speaker again.